or rainy glass, or even gemstones. Funny thing is, looking at how they're arranged as families of planets, we don't see a lot of exoplanet systems that look like ours so far. Many are arranged quite differently, so we might actually be the weird ones. Some planets are closer to their stars, some are super far. Some even orbit multiple stars. Imagine having 2 or 3 suns in the sky. So why do we study exoplanets? Well, our interest in finding worlds with life on them is a big factor. We want to know more about what makes a planet a place with all the right ingredients and conditions for life, what scientists refer to as habitability. How does it happen? How common is it? We think the most life-ready planets are the ones most similar to Earth, with a range of qualities that include similar size and composition to our planet, and being at the right distance from their stars to have liquid water on the surface. These qualities are really challenging to observe from so far away, but we're working on it. Exoplanets teach us a bunch of other things too. Studying other planetary systems helps us better understand the story of our own planet family, including Earth. Scientists detected the first exoplanets in the 1990s, but now we're finding tons more, thousands so far. We're studying their atmospheres and even making weather maps for some. We're surveying exoplanets to understand all their variety. And the more we learn, the more it powers our curiosity. The more we want to explore exoplanets, planets outside our solar system.
Okay, I guess we are done with the video. Just a minute, I need to check. It says recording has stopped. Is it still being recorded? Can someone confirm?
It says that it's being recorded.
Okay, cool. Then let's continue. Yeah, so this video gave you a crux of our entire session. But yeah, we'll get into detail of most of the things that this video said and something more. Also, one more thing, one more specialty about this session is that I have a surprise for you all towards the end of this session. And I mean, you guys must be at your homes or somewhere you're just sitting and watching this online lecture. But don't worry, it's not going to be just a lecture. There is a surprise, as I said, for you all in the end. We are going to go on a crazy trip and you're going to have fun. But before that, before going on a trip, let's get some information. Otherwise, you won't understand what's happening and you won't appreciate the trip. So before the first thing, if you want to understand something in basic sciences, is classifying like anything. And as we all know, this idea was first started by anyone. Can anyone name like who started this idea of classifying, not exoplanets in general? Who told that classifying will make things easier? Come on, it's a very famous name, very simple name. It's in
biology. It was Aristotle that was supposed to be the first one.
okay. And anyone in chemistry? Classifying as in studying properties of something by classifying. Yeah, obviously, yeah. In biology, we know. It is Mendeleev's periodic table, which was the most famous classification and helping us understand that like there are properties in periodicity. So that's not what we are studying here now. I was just asking a name to you guys, but yeah, it's great to know that and let's continue with our classification of exoplanets just to study them in the proper way. So as you can see on your screen right now, all the planets that we see around in our galaxy. Yeah, I should mention this fact that we have spotted lots and lots of exoplanets till now, but most of them, actually almost all of them are in our galaxy yet. So we are yet to discover planets which are outside our galaxy. We have discovered a few, I guess 1 or 2 in Andromeda, but yeah, there could be a lot many planets. It's just that those are a bit difficult, but we sure will at some day. So all the exoplanets that we know of can be classified in these 4 categories, which are gas giants, super Earths, Neptune-like, terrestrial. Now you see these 4 classification, and then you see our own solar system. Now our own solar system is also, it has a sun and it also has planets. So if you are classifying all the planets that you see around in these 4 categories, you should also be able to classify planets in our solar system in these 4 categories, right? So can someone just quickly, think about what all planets can be classified in which category in our, like from our solar system? And if you do that correctly, you will notice something very strange about our solar system. It's up to you. You can call it strange or special. So just how many gas giants do we have? How many super Earths? How many Neptune, like how many terrestrial? Just think about it. You can. It's okay to be wrong. It's good to be wrong. It's fine. And it will be better if you all don't Google it and stuff. Anyone? No one? Okay. Yeah, we got an answer, which is correct. Any more answers coming up? Okay, so we have some answers here, and as someone pointed out, so the first 4 planets are terrestrial planets, and then we have 2 gas giants, and we classify Neptune and Uranus in Neptune-like planets. But there is something really interesting in our solar system. I mean, whoever has classified the planets, like in the chat box, you must have noticed this. Everyone else must have noticed this. What is it? Something in this classification. Exactly. Exactly. Now imagine like if planets are randomly created. So if you take something out of something, I mean, if you take a sample out of a random distribution, you expect that you will find all types of planets, right? But somehow we don't have any planet of the form of like which can be classified in super Earth category. And I will really urge you guys to maybe after the session or whenever you have some time to just try to find out why is it so that we don't have any super Earths in our stellar system. Notice that I'm not using the word solar system. I'm using our stellar system because we are not really interested in solar system for this session. Okay, someone has asked why is one classification Neptune like, whereas others are more general. Well, one thing which I'm not really sure, I don't know the exact answer, but one thing which I have noticed, like while studying astronomy, is that we astronomers are very poor with naming. We just like to name, things the easiest that we want to. So we know that gas giants are made up of gas, and Neptune, like what exactly? I mean, what exactly can we name Neptune-like planets? These are icy planets, but then there are other icy surfaces as well. So they thought like it's easier to name them Neptune-like. I'll on this line, I'll tell you something interesting as well when it comes to nomenclature. So we astronomers are very lazy. We will design the biggest and the greatest telescopes on this Earth to see the furthest object possible. But while naming them, we are not going to take a single effort. So like, or I guess it's European Space Agency, and there are some other space agencies which are contributing in building a telescope which is of 30 meters. It's a very famous telescope that is being constructed. It is like ground-based telescope. And can someone guess what are they planning to name it? like it is technologically very advanced. It will help us see a lot further than we have seen from ground-based telescope. So, and they're putting a lot of effort in that, and lots of space agencies are involved. But exactly, Preetham has answered exactly. It's called TMT, 30-meter telescope. And then these guys decided to build a big telescope, like yeah, a very big telescope. And guess what they named it? It was called VLT, very large telescope. So yeah, that's what we keep on doing. We don't like naming. We don't like giving much time on naming. So that's why it's called just Neptune like. And someone has asked that what actually are super Earths. So just keep patience. We will go through all these 4 categories one by one, and you'll understand. So let's continue with our first classification, which is the gas giants. And I'm not going to read whatever's there in front of your screen. So you can just read and understand it yourself. It's just that we all very well know that what gas giants are, because we have 2 gas giants already in our solar system. We all know about Jupiter and Saturn, and I'm pretty sure almost all of us have observed all the gas giants. Yeah, well, when it comes to naming of exoplanets, we are not, we don't let it go as easily as we have named like other stuff like telescopes and stuff I mentioned. Yeah, anyway, so the gas giants, as we know, are composed of gases, and a special definition that we should focus here are hot Jupiters. Hot Jupiters are also something that we don't find in our solar system. What are hot Jupiters? As written, gas giants which are actually close to their stars. And on the right side of your screen, you can see one of gas giants, 51 Pegasi b, and some details about it. One thing that I want to mention here is that the units that we use when it comes to planets, we don't, whenever we are measuring something about a planet, like let's say, for example, a planet's radius or planet's mass or something, we don't use SI units like kgs or like meter. It makes sense, right? It's like sizes are too big. So what we do is we measure them in the units of Earth radius, or like if it's too big, sometimes Jupiter radius. It's usually Earth radius and Earth mass and stuff. And for stars, we do the similar thing in units of solar mass, solar radius. Another interesting thing that you see on your screen is the naming of the planet. It's 51 Pegasi b. So there's a proper format in which this planet has been named. So, can anyone guess what this means? 51 Pegasi b. Like, I don't know how to ask this question exactly. Just that, do you know something about this naming or 51 Pegasi b? There's a very special way exoplanets are named. There are so many planets that you cannot come up with. You cannot come up with so many names. So they just try to, I mean, it seems like a code, but like the code that is mentioned there, it has a proper meaning. And they can name some planets, but not all, like with common names. Just like if you go around US, Canada, you will see, city names being repeated. So we don't really know what it is. Okay. It's not about Pegasus or anything. Basically, 51 Pegasi. I'm not really sure how 51 Pegasi was named. I hope it wasn't named after Pegasus. It might have been named. See, usually it's named after a mission which found out that planet, or it's usually named after something which found out that planet or something. My point was the B that you see in the end. So 51 Pegasi is basically name of the star to which this particular planet belongs to. And the B that you see, that B signifies the planet. And as you go further, you will find out that this is the format in which all the exoplanets are usually named. They start with the name of the star, and which is followed by a particular letter. Now, what does that letter signify? The letters are named as, B, C, D, E. So these letters signify how far away, not in terms of like, not mathematical distance, more like comparative distance, relative distance between, I mean, if a system has multiple planets, so which planet is the closest will be named as I mean, the order in which these planets are named is in terms of how closest they are. So there will be B, C, D, E. The particular planet you see on your screen right now, it's called 51 Pegasi B. So what do you think? Like, is this the closest, second closest, third closest planet to its star? What do you think? What does B signify? Yes, someone has mentioned second closest. Any more answers? More second closest. Okay, yeah, let's continue. I wanted to say that B does not mean second closest. B actually means first closest. It is the closest planet to the solar system. Now, where did A go? So basically 51 Pegasi A refers to the star and B will be the first planet. Similarly, C, D, E will be the second, third, fourth planet. So that's how it is named. And we'll continue. Coming to super Earths, a very special category of planets, something that you don't find in our solar system, and we have discussed this before. And yeah, it's called super Earth because again, like why to name it something very complex? We have Earth. These are super Earths, something which are like bigger than Earth, but are not yet gas giants. And as you can see, Bernard star B, and now you know what B is, which was discovered like very recently. So one thing is that most of the exoplanets have been discovered very recently because of difficulties in the detection method. Then the third category would be Neptune-like planets, which is supposedly very famous in this particular lecture because people have been asking questions. And an example of Neptune-like planet in our solar system, obviously, it's Neptune. No need to ask. And then some basic properties of this particular example that are seeing Kepler 1655b. And then the terrestrial ones, our favorite planet. Why? Because of course, because we live on one. We live in a terrestrial planets, and the reason we are able to, sit on our chair is because we are on a terrestrial rocky planet. But there is one more reason why this particular type of planet is like particularly interesting for all the astronomers who focus on exoplanets. I think we all know the answer because of the purpose why we study exoplanets. Terrestrial planets are like the most favorable for that. So yeah, enough of the information, and now let's continue to our next section. I told you guys, remember that this session is about data. So this is the first time that we are actually seeing some data on our screen right now. And this will also show us the why data is very, very, very important and why it's not just about, science fiction, why it's not just about us reading and just being amazed by things. A long time ago, I don't know who, but there was this guy who suddenly thought of something very weird. He thought that let me just, try to plot. I mean, of all the planets that we knew at that point of time, he thought that let me just try and plot these two things that you are seeing on your screen right now. So on x-axis, he plotted, he used planet size. On the y-axis, he used number of planets. You can use per star or even total number of planets work as well. Just that per star helps you in as you can see, the units, it's like in 0.000, 0.02 and stuff. So when he plotted this, I mean, what was he expecting? Whenever you plot something random, you expect a Gaussian plot out of it. I'm hoping you guys know what Gaussian plot are. Okay, for the people who don't know, Gaussian plots are more like in the center, there is a peak and then it just like, spreads away. This is a usual Gaussian thing. That's what you expect from any random plot. That's what this guy was. Yeah, Belker. Yes, yes. That's what we all were expecting. That's something which was very obvious. But when this guy actually plotted, he saw something very, very, very weird in this plot. Can you guess can you guess what it is? I mean, the plot is right there in front of your eyes, and it's not very difficult to see. more than two peaks. Yeah, I mean, it's fair observation, two peaks, but more than two peaks. The more interesting part is the valley in between. I mean, it's like really interesting to think. You find lots of planets which are, yeah, that is fine. Okay, imagine if this valley was not there. As someone has mentioned that both peaks are dissimilar, so I'm answering to that question. So imagine if this valley was not there, it still would make a bit sense. No, a thick peak would have made sense. But we find planets, lots of planets, which are like in this domain of 1.0 to 1. Let's say 1.5 Earth radius. And then similarly, we find lots of planets on the bigger side. But somehow we found very, very few planets in between this range that you are seeing, between almost 1.5 to 2 Earth radius. And this surprised people. I mean, what could have been the case? It's very interesting to think about. That's what happens in science. If you are a scientist, you just don't ignore certain results because you never know why is it happening. I mean, the first guess that someone will have looking at this would be that, okay, it could have happened because, because of somehow we might have observed more planets in Earth's category and more planets in maybe, gas giants. But like, it's very weird to think, right? I mean, if it's a trend, it makes more sense. If like we are able to see gas giants, it makes sense. Yeah, that we don't have enough technology to see smaller planets, but we are seeing smaller planets. And we are seeing bigger planets. It's just that in between that we are not seeing. As you can see, like this gap was called as Fulton gap. And again, I will urge you all to just somehow find out the reason why like we are not getting this. And one important thing is that we still don't know the exact reason, or there might be, I don't know the exact reason, but we have like multiple guesses why this could be the case. And one of the guesses, of course, that we have not find it, which I find very, very weird. But the answer lies in the planet formation part of it. So just open your mind and think about why this could have happened. And by the way, such type of plots are called as bimodal plots. You must have studied mean median mode. So mode is basically like the peak. I mean, this is a histogram, by the way. So the peak, it's called mode. So that's why this plot is called bimodal. It has two modes.
Could it be due to the density difference in the planet types? As the size is differing, so could be their density, which might have
As the size
affecting
is
the
differing, so as the size is differing, so is their mass. So density could be the reason, but density might not be the reason. As you see, Jupiter is like a lot more dense, but again, Saturn, it's like even less dense than water. Both of them are gas giants. So as the size increases, mass also increases. I will just urge you to look into it. What exactly was the reason? I mean, people have worked on this. This has been there for a very long time. So solar flares reduce the size of planet. There are hot Jupiters, which are really, really big planets and very close to their stars. So just keep a bit patience and yeah, first think and then try to find out. It will be interesting. And like we can discuss this sometime later over, WhatsApp or something, or let's just see. Now let's continue because I think we are running a bit late. Okay. Something something which is very important whenever you are studying science, any form of science, I will really urge you all to whenever you're starting working on a project or whenever you're starting, studying something, the first question that you should ask anyone who's teaching you, or the first question that you should ask yourself is why. This is something that people don't usually do. They don't ask the question, why am I studying this? Why is this important? So it's like very important to know. Once you know why you are doing something, then like, you will be able to do that particular thing in a much, much, much better way. And if you're not answering the question why, you are just, you're no better than a corporate worker. I'm sorry if that offended someone, but you are just working. Someone is giving you some work and you are just working. So we have spent almost more than half an hour over types of exoplanets, what exactly exoplanets are and things like that. But we haven't yet answered the question. We haven't yet wondered out why are we even studying this particular subject? Why not something else? So there's a reason why I personally like this, and there's a reason why we chose this. And we will see what it is. And the answer is also in one of the quotes that is mentioned by Carl Sagan, that somewhere something incredible is waiting to be known. So yeah, exactly as someone said. So okay, like I think some of you might already know that why are exoplanets, so popular. So yeah, let's just continue with it. Drake equation. Yeah, actually, before Drake equation, a little bit of background about to the people who don't know. Uh, Two of the biggest unanswered questions in astronomy or cosmology that we know of right now are: first, are we the special ones? Is it just we? Or is there another civilization living somewhere? Is there a possibility of life somewhere? And trust me, people might tell you that this question, I mean, science fiction writers have used this question a lot for their imagination, but just trust me, scientists are working on this and it might be possible. I mean, just a raise of hands, how many of you think, I mean, this universe is so vast that how many of you think that, somewhere something it's still out there? Like, it's not just us, we are not special. Yeah, I see lots of hands being raised. Yeah, it's really interesting. I mean, people, when you talk about this to people, people might say that okay, like we are living in a dream world, a fantasy world, but I personally still believe that Earth is just one of the planets. There are lots and lots of stellar systems. There are lots of planets, so there is possibility of life elsewhere. And I mean, it's more possible to have a life than an intelligent life, but it still is possible. And I saw some discussions about this in the group as well. So yeah, that's why this topic is very, very interesting. And yeah, I mentioned two things which are like two of the biggest mysteries of astronomy at this point. So I should mention both. The second mystery is, as you all know, dark matter and dark energy, like which forms about what at this point forms about 69 or 70% of our universe. And we still don't know what exactly it is. Yeah, but we are not going there today. We are just probing into the first particular thing. And we are not probing as in we will not like study completely about what it is. It is just to let you know why exactly are people interested in exoplanets, just to find a new friend. We are never tired of finding friends. And as I keep on saying that even if it is science fiction, you should not take it lightly, because today's science fiction is tomorrow's science fact. Let's continue now. I hope it gave you some motivation for this particular session. Coming to the Drake equation, it's not, as I said, it's not that scientists haven't worked on this particular aspect. So it's important that we see a bit of work that has been done. Now we are all after uh, life. We are all looking for if life is there or not. So we have this particular equation, and this equation, by the way, I should mention, is not an equation which has been derived from data. It is and it is not an astronomical equation. I would say not a physical equation. It's more of a statistical equation. This equation just tells us about the probability of finding life, and it also helps us give an idea of what all we need to do, the steps that we need to take to find life. And I hope that you can read what's there on the slide, but if you cannot, I'll just help you all with it. So the number of technologically advanced civilization will be equal to, it's very, very logical criteria in which this equation has been divided into various terms. Yeah, let's not go into Jadoo and stuff. So, and let's focus on the science of it. That's why I said it's very easy to get swayed by science fiction, but we have to understand that we are looking this through our scientific minds, not science fiction minds. So if you want to find number of technologically advanced civilization in the Milky Way, we will start by a bigger circle. What is the bigger circle? Obviously, what is the most important thing which is powering us, powering me, powering you, powering us all? It is the sun ultimately, right? So the most important thing is the star of that particular solar system. So the rate of star formation in the galaxy is the bigger circle that we need to know first. And then we come into the circle inside it. Once we know star forming galaxy rate of that particular galaxy, then like inside the star, we see that how many of those stars have a planetary system, because nothing as in ki we are expecting no life can exist on a star. And then after that, once we know that these are the stars which have planets, next we go to how many planets have an environment which is suitable for life. That's the reason like we don't find life very easily, because we need to find the planets which have environment suitable for life. And out of this, then we come to the fraction in which life actually appears. Because there's a big difference between being able to do something and actually doing something. And this quote was not about Drake equation, it was about life in general. There are times when people feel that they can do something, but it matters what they actually end up doing. Anyways, yeah, this is not philosophy, so let's continue. I'm sorry. And then on the planets in which life actually appears, we also have to find out if that life is an intelligent life or is it just life. And then is it like enough? It seems like it's enough, right? Life and then intelligent life. But like it isn't. Our aim is to not just our aim is to know that that life exists. And how will we know? Even if it exists, it should somehow be able to contact us. That's how we will know, right? Or we should be able to contact them. So out of the fraction that life exists, we also need to find out the fraction of which have developed enough technology so that they're able to contact us. Now even this is not enough, because they might have developed technology, but they should be living so close to us that their signals are able to reach us. Here, I would like to mention a definition of observable universe that you might know about. So imagine if a civilization lives very far away, like it's so far away, you all know that universe is expanding. So at some point, the speed of the expansion of universe is more than the speed of light, so that anything which is outside that particular boundary cannot send a signal ever. So there's no point even if life or something exists there, because for us it simply doesn't. So this is also a very important point. Now you see a big gap in between in the first two terms and the rest of the terms. The reason for the gap is very obvious. It's because the first two terms we already know very well. We know that the star formation rate of galaxies, it's very easy. And by the way, you will work on this star formation rate will be very important when we'll start working with some data. And then we also know which all star formation galaxies have some planets. And the any term, actually, currently we are very much focused on the number of planets which have an environment suitable for life. And the research is still going on. Rest of the terms we are not yet aware about. I hope we aren't, because at times there are people who don't share stuff with rest of the world. And another video for you all.
Planet called Earth. Earth is habitable because it had the right conditions and ingredients to enable life as we know it to evolve and flourish. And one of the most important factors in making our blue planet habitable is the wet stuff itself, water. It's kind of extremely important for life. When it comes to the search for habitable exoplanets, planets outside our solar system, we think the ability to have liquid water on a planet's surface is just as important for those worlds. There's a handy concept astronomers use to help them figure out where to look around any given star for exoplanets that just might have the right stuff for life. It's called the habitable zone. It's the distance from a star where a rocky planet with an atmosphere could have liquid water on its surface. In our solar system, the habitable zone extends from around the orbit of Venus to around the orbit of Mars. Earth happens to be nice and comfy in the middle, but it takes more than just a good location. Orbiting in the habitable zone does not guarantee a planet will be habitable. After all, the moon is right here with us, but it's certainly not habitable. Sorry, moon. The location of the habitable zone depends on how big and bright a star is. The nearest star to our sun, Proxima Centauri, has at least one planet in the habitable zone. But because Proxima is much smaller and dimmer than our sun, its habitable zone is way smaller and closer to the star. So every star has a habitable zone, but that doesn't mean there will be planets there. For example, the star known as Kepler 90 is similar to our sun, and it too has 8 planets. But they're all huddled super close to the star, well inside of the habitable zone. But the longer we look, the more likely it becomes that one day we'll find another little blue, water-covered planet right in its own comfy habitable zone. And that would be a planet worth a closer look indeed.
Another video of NASA, which I hope helped you all understand what it means by what exactly are we looking for and what it means by habitable zone. And this covered basically everything that is going on as of now, the research that is going on. And yeah, whatever you saw in that slide, this is just a description of this. So habitable zone. Now, what exactly is habitable zone? You saw in this video, how do we define habitable zone? Because anything that we study about, we need to define it, right? In science. So you must have seen already in the video, how do we define a habitable zone? So I just need some answers now. What is one factor which we use to define habitable zone? And please don't use Google. Temperature. In a way, yeah, you guys are right. I mean, distance from the star will determine temperature, but that video actually mentioned a definition. Exactly, exactly. As someone mentioned. Yeah, so this is the most important factor. Okay, one thing that I want to mention, one is written terrestrial planet. One thing that I want to mention is that habitable zone has nothing to do with the like if there's a planet in that region or not. You will see in future that in future as in today only, that there are habitable zones which does not have any planet, like which is very unfortunate. We define planets after we define habitable zone. Habitable zone is just an area at a particular distance from a star at which, as someone said, liquid water can exist. Existence of liquid water is very important because as you proceed, and if someone has studied biology, they will realize the importance of having a polar solvent for life to exist. That's why at the distance where liquid water can exist, that is from a particular star, we define habitable zone. Now it's when I say this, it's also important to note that like existence of liquid water will be determined by temperature, right? So and what will determine temperature? It will be determined by the star. So different solar systems have different habitable zones. For some of them, it's a bit closer. For some of them, it's a bit further away. For some of them, it's a bit bigger. For some of them, it's a bit smaller. As you can see on your screen right now, it depends upon how big the star is and how radiative the star is. Like what's the temperature dependence, how luminous the star is. Uh, okay, there is one term which combines both temperature and I mean there are two factors, right, which I mentioned. First one was temperature, another one was size. So there is one factor which combines both temperature and size of a particular star. Do you know that term? The term is very frequently used in astronomy for observing. I mean, I won't expect you to know, but it will be great if someone knows. It's related to light. Light flux that we measure, it's related to that. Yeah, it's okay. No worries. So the term that I'm talking about is luminosity. Luminosity combines both its like the size of the star and the temperature dependence of the star. And yeah, let's just continue with that. Now, we have seen why exoplanets are important. We have seen like what exoplanets are and how they are like classified in different parts. So now it's time to move on and get your mind out of all the sci-fi stuff that you must have thought about till now or whatever we did. Now, another very interesting question that we should ask ourselves is when you look at the night sky in the star, assuming that some of you don't live in the cities where looking at night sky, you don't see anything apart from smoke. And obviously assuming that you're not living in Delhi. So when you see at the night sky, you see pointed stars, right? That's what you see. I mean, it was when someone told me for the first time, no, that our sun is also one of those stars. It was very difficult for me to digest. But I mean, obviously, we know it's like true as of now. But what I wanted to say is that the stars that we see are already so tiny pinpointed objects. So have you ever thought that how do we even know that if those stars have a planet with them? I mean, if you look at even our solar system, you will see that the sun is such big of a star. And if you compare sun's size with Earth's size, you will realize how smaller our Earth is with sun. And we have no reason to guess that Earth is like the smallest planet ever. And in other solar systems, the planets are very big. So has it ever crossed your mind how exactly, like, did we detect planets which are, I don't know how, I can't even say how to even compare in like those tiny, tiny stars. Even if you use a telescope, you will still see stars as tiny dots only. It will be a bit bigger, but it will ultimately it will be a dot only. It's very, I'm pretty sure you can't see star with the size of the sun. Star as in some other star. So now, but yeah, it's a fact that we know lots of exoplanets now. So now we will get into the methods which are used to detect exoplanets. And as you can see on your screen, there are lots and lots of methods. But I'm pretty, yeah, we won't go in all of these methods because it will just become boring if we just keep on, talking about each and every method. And this is not a professor lecture. I hope there isn't any professor or some who has joined this session. If there is, I apologize. Yeah. So exoplanet
Hey,
detection.
Ganga.
Okay, was someone asking something? Yeah, I guess someone has raised their hands. Do you have a question? Yashika. Yashika, do you have a question? Okay, it might have been my mistake. Anyways, so yeah, exoplanet detection methods. And let's get started with it. And again, focus on your screen because again, we have another video for you to see how our first method works. This first method is the most important method in exoplanet detection, and you will notice why is it so. Please switch off your mic if you don't have anything to speak. So, what did you understand from this particular video? One of the very famous methods of exoplanet detection, the transit method. As you saw in this video, there was this planet which was passing through this star. Now, what did we do? We can't see that planet. So we like employed a very interesting method. What we did was, I mean, there's a star and we can detect the light coming from that star, right? As you can see, this plot on the left side of your screen, the light curve it's called a light curve. We measure the light as a function of time. And there was this star there, and we were kind of measuring a constant light coming from it. By the way, in real life, this plot is never a straight line, as you can see. This has just been cleaned a lot just for your explanation. But what happens if that star consists of an exoplanet? It's very interesting to see. We have a constant light coming through it, but the moment this passes through, yeah, the moment this passes through in front of us, what do we see? We see a dip. See, the moment it passes through, like it passed in front of the star, we saw this dip. So this helped us think, why is there a dip? No, there is one more important thing about this particular method. This particular does not only tells us that there is a planet around, it also tells us something more about that particular, it tells us some property of that particular planet, which we will see in the next slide. But yeah, just to let you know that transit method is like the most important method, not just because of this particular thing where you see a dip, it is because of its other properties. Also, I would like to say at this point that I'm hoping that all of you guys who are in there in this session are budding scientists. So this particular method won't work if you simply ignore certain things. As I said, this plot is never as fine as you see in the screen right now. Even the straight line has like some bumps going up and down, and like there's this one dip which is a lot more deeper. So if you just think that all these dips are just some noise in your data and you will remove this, you will never detect an exoplanet. So it's very difficult, and it's very important that you, before eliminating any point, you just focus on it for a very long time. That why is it so? Is it really noise, or am I just removing a possible discovery? That's how all discoveries have been made. So never ever, just my advice, never ever discard any point just because you feel that it is showing some weird behavior. Coming to the next thing, now you will see why this particular transit method is not just another method, and why is it a lot more important. As you can see, there are two planets which are like revolving around its star, and you see that if a smaller planet passes, it's like very obvious, right? If a smaller planet passes, the dip is smaller, but if in case a bigger planet passes, the dip is a lot more. So what does this tell us? This tells us that the data that we get, the amount of dip that we get, also helps us know about the relative size of the star of the planet. What if a planet consists of multiple? Sorry, I'm really sorry. What if that star consists of multiple planets? If that's the case, then we will see multiple dips. And again, multiple dips will again look like a noise, but don't ever discard it. Telling from experience, one of my friends discovered an asteroid passing from this from very close to the Earth, which NASA missed just because she decided not to ignore a certain anomaly in her radio astronomy project. And she is now working in Caltech. So never ever do that. So this is the transit method. Coming to the next most important method, which is the radial velocity method. And you will see what happens there. Okay, one thing I hope you guys have heard of is redshift, blue shift, at least Doppler shifts in terms of sound, at least. You must have studied this in your 10th, 11th, 12th. So this theory is very important in understanding the radial velocity method. How? Now you are seeing a star and then you are measuring the light which is coming out of it. But suddenly you start seeing that the light that you see is not like it doesn't have a particular wavelength. It is red shifted and blue shifted at times. Now, what is redshift and blue shift? In short, if something is moving away from you, the light that you receive from it is red shifted. It gets shifted towards the red end of the spectrum. And if something is moving towards you, it gets shifted towards the blue end of the spectrum. I mean, you can read more about it later on because I don't want to spend a lot of time on this. I'm just assuming that you know this. And this particular method is employed. Now, how is it employed? If a star, one important thing also that you must have studied in a two-body system is that whenever there are two bodies, it's not that one body revolves around another body. It's always that two bodies revolve around the common barycenter. So if there's a planet and there is a star, although the sizes vary a lot, still it's not it's not essential that in fact, it never happens that the barycenter of this system lies exactly at the center of that star. It never happens. It is somewhere it might be outside the star, as in our case, if for our solar system, just because of the presence of Jupiter, our solar system, the common barycenter lies a little bit outside the sun's surface. So if a star has a planet, it's not just the star, it's not as a planet which is moving, it is also the star which is moving around the common barycenter. So what happens if like this is happening? If a star is moving, there will be time when this it will come towards you, and that is the time when you will see that light will be blue shifted, and then there will be one time then it will go away from you. That at that time you will see that it is like red shifted. Now we all know that the universe is expanding, so light that we get in general from any star is usually red shifted. So how do we distinguish between that red shift and this red shift? It's very simple. Cosmological redshift is just a redshift. Everything is moving away from you. But this thing that you get, it is periodically red shifting and blue shifting. It is like Doppler redshift and blue shift. That's what lets you know that, okay, the star is not stationary. It is moving. How could it move? So it could move if, and I'm using the word if, like focus on that. I'm not saying that it has a planet. It could have a planet. it is very important because while doing data analysis, we never said using one method that we have detected a planet. We always say that we use it on candidates. We always say that this could have a planet, and for a final detection of a planet, it has to be a combination of multiple methods that should show that okay, there is a planet. Now let's see another method, which is gravitational microlensing. So before this, some information about what gravitational microlensing is, what lensing is. What happens? Okay, we all know that you must have heard of relativity, right? Albert Einstein. Half of you might have also seen Oppenheimer yesterday, so you must have seen Albert Einstein, or you might be seeing it today or tomorrow sometime. So Albert Einstein, relativity, general relativity. What is that? It is simply matter curve space-time. Now, this is the thing which is employed in gravitational lensing. So what happens is that if a very massive object is present, it will curve space-time around itself. What happens if space-time is curved? As you can see in the plot, you can see that the fabric of space-time is a bit curved. Now imagine if there's an object behind this particular big object and it is emitting light. Object, let's say both are stars. This is a big star which is in front of you, which is like which has curved space-time a bit, and there is another star which is behind this bigger star, and you're receiving light from it. Now light from it won't be coming in a straight line since light follows the path of the space-time, right? So since it is curved, it will follow this curved path. And what happens is that like instead of coming in the straight line, the light will a section of light will come, let's say, for example, from above it and then from below it, and then it will merge here. So the image that you see of that particular object which is behind the bigger object will be a lot bigger and brighter. And at times you see multiple objects as well. This is known as lensing. Like the star in the front is star or a galaxy, anything in the front is acting as a lens for the object which is behind it. At this point, I should also mention the story of, I guess it was Arthur Eddington only, who just, when Einstein proposed his general theory of relativity, people were very eager to disprove that theory because it was not very evident at first. So any theory can be easily disproved if you find one experiment. Yeah, as Anita mentioned, eclipse. If you find one experiment which can simply, which simply does not follow that particular theory. So it's very easy to discard it. So that was the famous voyage that Eddington went to discard Einstein's theory. And like as Anita is mentioning about the eclipse. So obviously if the sun is there, we won't be able to see anything behind it, right? I mean, in the morning time, you can't see any star behind it. So one way to see the lensed light is during eclipse. So they went there, and instead of actually disproving relativity, Eddington ended up actually proving that relativity is true. It's so interesting that sometimes you're trying to prove that something is wrong, but you end up proving it. Happened when Albert Einstein was never fond of quantum mechanics, but he was one of the person who gave an experiment which actually proved quantum mechanics. Anyways, let's not go into that. So yeah, this is gravitational lensing that I said. It is happening because of gravity. That's why gravitational lensing. Now, what is gravitational microlensing and how does it help us detect a planet? Let's see that. If you look at this particular curve, again, we have a time curve, light curve, I'm sorry, that I mentioned before. Now, what is happening? As you can see, this is an object passing in front of it. This is the bigger object, which is curving space-time. And there is a star in behind, due to which, as you can see, the flux of the light has suddenly increased, right? We have just seen how the flux increases because the light combines. So if the flux is increasing, we know that there is an object behind it. But there is something very interesting that you might have noticed in this plot. I just pause it when after this plot is done so that you see it. And I want answers now. I want some of you to tell me what is something very interesting that you see in this plot. I mean, you do expect the peak to come, but you see something else as well. This is where I should stop, I guess. Can someone say, mention what is something that you are seeing in that particular plot, which is not very obvious? If you want, you can switch on your mic or you can type.
A peak higher than the general peak at the starting of the peak.
Yes, great. It's not about being higher. being higher is not important. Just presence of this small peak is very important. And this peak is very, very, very small. It's not like, I mean, as you can see, one peak is like starting from the base and it is going till very top. And this is small. What should I say? There should be a term for this. Yeah, never mind. You all can see there's a small peak. Now, if there's a small peak, one wonders why is it? Is it again, is it because of noise? Because this small peak can be easily ignored. But there could be something else. And that's what it turned out to be. Yes, people found out that, and that's when, there are things which seem very illogical till the time you don't know it. Once you know it, things start seeming very logical. Imagine what if the star in front of it that we are seeing had a planet. So it's not just the star that would curve space-time. Planet will also curve space-time. Obviously not as much as the star, but it will still do it a little bit. And that's what gives it this little dip that we see. And this little bit, a dip. Okay, why am I using the term dip again and again? It's not a dip, it's a peak. That we are seeing, it says that, okay, this star is not alone. It could have something else. So again, there could be a planet. Another method, direct imaging, a very obvious method, won't spend much time on that, is just trying to image a planet directly. Again, you could not see the planet till the time it had, till the time that you could see the star completely. So we somehow try to cover that star and try to see there's a planet nearby. This method is very popular these days because it is very, very difficult. Other methods are comparatively easy. It's very, very difficult, but people are working on direct imaging. Because if we are able to find out planet using direct imaging, it will be a direct evidence. Like it won't be like there is something we can say that it is a planet using this method because we are directly seeing it. Astrometry. Astrometry seems very similar to one of the methods that we saw before. Which one? Which method did we see before, which is like a bit similar to astrometry that we have seen? Obviously, there is a difference. That's why it's a different method, but we're employing the same effect. Yeah, redshift. So basically, it was known as radial velocity method. So what are we doing here? As you can see, what do we do here is that, again, we measure the distance of the star as relative to other stars which are present. Now we see that this relative distance is changing. If this relative distance is continuously changing, it's evident that because it's not that easy to see that star moving, right? So if the relative distance is changing, it becomes very evident that, okay, this particular star is moving. That's why it's changing. And if it's moving, the planet could be present. And yeah, we are done with the some of the exoplanetary detection methods that we saw. There are lots of methods, but like we didn't go into all of them. We just went into very important one of them. Now, next we'll go into some of the exoplanets mission. This part is very theoretical and just for your knowledge sake. So I will not just spend time on it. I will just tell the very important part, and you can just read it on the slide. It's already there. Before starting, okay, I just want you guys to name at least one famous mission. One famous exoplanet mission. Exoplanet missions are basically space-based missions which are detecting exoplanets. So any one mission that you guys know. And I hope you guys know at least one mission. Right? A very specific mission Siddha mentioned. A very famous mission, the recent most mission. Yeah, I was expecting JWST for this recent most. JWST is not like specifically concerned for exoplanets, but yeah, a part of it is specifically for exoplanets. And let's just see now. Starting with the oldest. And I'll still say one of the best space missions we have ever had. The Hubble Space Telescope. Have you seen the Hubble Space Telescope in the night sky? You know, it's very easy to see HST. It's so close to the Earth. Whenever you are seeing, I mean, to people who might have seen but might not have realized it's HST, I will just say that whenever you see a star moving around the night sky and it's moving slowly, it's not a star because stars or meteors does not move slowly. It is usually a Hubble Space Telescope, as Ankur mentioned, it's usually either Hubble Space Telescope or ISS. You can use Stellarium to find out which it is, but yeah, it is always visible, and it is like one of the most oldest space mission As you can see, it was launched in 1990s and it is still giving us very, very, very important data. Although we have JWST now, but the position where JWST is it's like very far away. HST is very close to us. So it's important to understand the importance of Hubble Space Telescope. And then as someone mentioned, Kepler launched in 2009, and Kepler is important. Kepler and the other telescope that we are going to see is important because of the data that we will use. It will be from these two telescopes. One important definition that you see is the second line, which I forgot to mention in one of the previous slides when we are looking into it. It's the Goldilocks zone. So the habitable zone of a particular star is also known as Goldilocks zone. And interesting thing about Kepler is that its mission ended way before in 2016, but it still got extended by the name of. Okay, I won't mention it now. I'll let you know this thing later. And the TESS mission, which is the most important mission, because the data that we will use, a lot of data, that data will be from TESS, Transiting Exoplanet Survey Satellite. As the name suggests, okay. Any ideas which exoplanet detection method does this mission use? Again, no need to search. What do you think? It's written right in front of you. We saw many exoplanet detection methods, right? So which method does it use? Exactly. It uses, as the name suggests, Transiting Exoplanet Survey Satellite. It uses the transit method to detect exoplanets. Yeah. Yeah. It's transit method, not just meth. Continuing to the famous JWST that we were talking about, the recent most mission, and the mission that got launched, and it's almost 1 year since JWST gave us, its first images, and I'm hoping that you all saw it. It was really beautiful. The deep field image was my most favorite image that was there. But in JWST, there is something very interesting. Should I ask this later or now? Okay, I will ask this now. You can think about it later. Just look at the hexagons that you see. Just look at this now, and I will ask the exact question later on. And JWST is again looking for planets around, and JWST is giving us more accurate data than Hubble Space Telescope, obviously, because it's advanced. And just a trivia question: do you know where at which orbit do we have JWST placed? A trivia, it's not even if you know or not know. If people who have read will know, and you might not know if you haven't. Yeah, as someone said, yeah, L2. So it is at the second Lagrange point where this is place of the Earth-Sun system. And I guess this is where we are done. And I'm sorry for such a long lecture, such a long single lecture without any break. By the way, don't leave. We are not done yet. We are done with this particular session. So yeah, I just hope that I didn't bore you. I just hope that you learned something out of it and you enjoyed listening and understanding, and your mind is at the level where you are thinking. It's very important for you to think, because you are gonna be a scientist, and who knows, you might end up discovering something really great and you might not remember this session. Yeah, anyways. So I want to thank NASA and SETI Institute for this session, because we have taken some of our contents from that. And a very, very, very special thanks to you all for being very patient and listening to whatever I said. And NASA, you all know, and SETI, do you know what SETI is? Someone? Does someone know? Okay, so SETI stands for Search for Extraterrestrial Intelligence. And it is an institute. It is associated with Berkeley. It's Berkeley SETI, which does this particular job. And trust me when I say it, that they have some results that they are not revealing. And if you get a chance to work at SETI, which I fortunately got at some point, you will find out something really interesting. So for that, just apply for some of their programs and try to do like try to get into Berkeley. You will find an interesting thing that has actually happened. Anyways, so thank you all for attending. Now it's 11:50. We have another part of session coming up, which will be from 12. We will take a 10 minutes break. And I hope you guys join on time so that otherwise it can get extended. If you are late, and I don't like usually extending sessions. So please join in time. We will meet exactly at 12 o'clock and we'll start exactly at 12 o'clock. So I hope you all join. And if you have missed this session, no worries. We have recorded this session. But please attend the next one. Next one won't be related to this one. So you can still understand even if you have missed this one. So we'll all see each other after a short break. And if you want, you can stay in the session, or you can just leave if you want, just join. If you'll stay, we can just have a chat, or else you can leave, up to you. And now we have to stop sharing. Pause the recording. Okay, there's no option to pause the recording. Let's stop recording. Okay, I'll stop.